And we conclude our look at number theory by looking at the method of indirect proof. So there's actually going to be two methods we look at. Now, recall that direct proofs start with the hypothesis of a statement, and then we make one deduction after another until the conclusion is reached. Indirect proofs, however, are more rounded, and the two types we study are proof by contradiction and proof by contraposition. So we start by looking at proof by contradiction, which is based on the fact that every statement is either true or false, but never both. So if we can show that the assumption that a given statement is false leads logically to a contradiction, an absurdity, or an impossibility, then we can conclude that our original assumption was false, i.e., the statement must be true. Now, the problem with this technique is we have no idea when or how the contradiction will arise. So the method of proof by contradiction: first, suppose the statement to be proved is false. So that is, suppose that the negation of the statement is true. Show that this supposition leads logically to contradiction, and then we can conclude that the statement to be proved is actually true. So let's go about proving that there is no greatest integer. So assume to the contrary that there is a greatest integer. Call it n. Right? So remember, the original statement was that there is no greatest integer. So we're assuming the negation. There is a greatest integer. Well, what this means is for all integers little n, we must have big N greater than or equal to little n. Now define big M to be big N plus 1. Clearly, big M is an integer. It's the sum of two integers. However, big N plus 1 is greater than big N. Well, this means that n is less n. But wait a minute. M is an integer larger than big N, but we just said that big N had to be greater than or equal to every integer. This is a contradiction. So this is the symbol that will be used to represent contradictions. Therefore, there is no greatest integer, right? Our original assumption that there is a greatest integer is wrong. So another one, we're going to prove that the sum of any rational number and any irrational number is irrational. So we suppose, to the contrary, that there is a rational r and an irrational I, such that r plus I is rational. Well then, there must be integers a, b, c, and d, such that r is a over b, and r plus I is c over d, where b is not 0 and d is not 0. This is by definition of rational numbers. So what we have is r plus I, which is a over b plus I, which is c over d. If we solve for I, we get I is c over d minus a over b, which is cb minus ad all over db. Now, cb minus ad has to be an integer because it is the product and difference of integers, and d times b is an integer because it is a product of integers. Furthermore, since neither b nor d is 0, their product can't be 0. So we have written I as x over y, where x and y are integers and y is non-zero. So this means by definition I is rational. But we just assumed that I was irrational. So we're saying that I is both irrational and rational. That is a contradiction. So our supposition must have been incorrect. So r plus cannot be rational. So r plus I is irrational, and the proof is complete. Now, proof by contraposition is based on the logical equivalence of a conditional statement and its contrapositive. Remember when we studied logic, we showed that a conditional statement and its contrapositive were logically equivalent. So what we do in proof by contraposition is prove the contrapositive of the statement and then conclude that the original statement must be true. So first, express the statement to be proved in the form of for all x in D, if P of x then Q of x. This is again typically done mentally. Rewrite the statement in the form for all x in D, if not Q of x, then not P of x. Again, this is typically done mentally. We then prove the contrapositive by a direct proof and conclude that the original statement is true. So typically what we do is we assume that the conclusion is false and work to show that the hypothesis is false. So for every integer n, if n squared is even, then n is even. We will prove this. Now here, look, I'm using a different word. I'm not using theorem. I'm using proposition. So proposition is used here rather than theorem because mathematicians often restrict theorem to especially important statements that have many and varied consequences, and use proposition to refer to a statement that is somewhat less consequential, but nonetheless still worth writing down. So really, a proposition is just a less important theorem. So by contraposition, suppose n is any odd integer. Remember, we will suppose the negation of the conclusion. Well, the opposite of n being even is n being odd, right? That's the parity property. Every integer is either even or odd. We then want to work to show the negation of the hypothesis. That is, we want to show that n squared is odd. So n is 2q plus 1 for some integer q. So write n squared. It is the quantity of 2q plus 1 squared, which is 4q squared plus 4q plus 1. So this is 2 times 2q squared plus 2q, right? We can factor a 2 out of these four terms, all plus 1. But 2q squared plus 2q is the sum and product of integers, and so it must be an integer. So n squared is 2 times an integer k plus 1, which means by definition n squared is odd. So we've now proven if n is an odd integer, then n squared is odd. So its contrapositive is true, which is the statement n squared is, if n squared is even, then n is even, must be true. And so the proof is complete. So we will conclude this lecture by looking at two famous theorems, two famous proofs. The first one deals with the irrationality of the square root of 2. So the statement is the square root of 2 is irrational. So suppose to the contrary that the square root of 2 is rational. So notice that we're doing a proof by contradiction here. Well, since we're assuming the square root of 2 is rational, there must exist integers m and n, no common factors, such that the square root of 2 is equal to m over n. Now this is actually true by a property we have not yet looked at, but it is an axiom, so we can just take it to be true. If we square both sides, we get 2 is equal to m squared over n squared. So this means that m squared is equal to 2n squared. Well, n squared is an integer. So we just said that m squared is even, which means that n is even. This was by that proposition. Therefore, m is equal to twice some integer k. So m squared is 2k quantity squared, which is 4 squared. But this has to equal to n squared, which means that n squared is 2k squared. But this means that n squared is even. So again, by that proposition, n is even. Well, thus, m and n are both even, which means they both have 2 as a factor. However, we assumed that they had no common factors, so it contradicts that assumption. Therefore, this assumption is incorrect, and the square root of 2 is irrational. So the next theorem has to deal with the fact that the prime numbers are infinite. However, we need another result in order to prove it. And that result is for any integer a and any prime number p, if p divides a, then p does not divide a plus 1. So again, notice I'm using a different term. I'm saying this is a lemma. Now in mathematics, a lemma is a generally minor proven proposition which is used as a stepping stone to a larger result. For that reason, it is also known as a helping theorem or an auxiliary theorem. So a lemma is typically a proposition that we need to prove another result. There are typically 2 ways to go about lemmas. You can either introduce them in the proof of the result that you need it for, or you can introduce it before attempting that proof, as we're doing here. In either case, you still need to prove the lemma result. So again, we're going to use contradiction. So suppose, to the contrary, that there is an integer a and a prime number p, such that p divides a and p divides a plus 1. So by definition, we have to have integers r and s, such that a is p times r, and a plus 1 is p times s. It would then follow that 1 is equal to a plus 1 minus a, which is p times s minus times r. We can factor out that p, and we have p times s minus r. So 1 is equal to p times s minus r. Now, s minus r is an integer. So we've just shown that p divides 1. However, the only divisors of 1 are 1 and minus 1. That was by a theorem that we proved in the last lecture. So p is equal to negative 1, or p is equal to 1. But this contradicts the fact that prime numbers are larger than 1. So this supposition is incorrect, and we have that for all integers a and all prime numbers p, if p divides a, then p does not divide a plus 1. And we can now tackle the second famous proof, that is, that the set of prime numbers is infinite. In other words, there are an infinite number of primes. Again, this will be done by proof by contradiction. So suppose, to the contrary, the set of prime numbers is finite. Then this means that there has to be a largest prime number. So we can list the prime numbers in ascending order: 2, 3, 5, 7, 11, so on and so forth, up until p. Now, let capital N, let big N be the product of all the prime numbers plus 1. That is, big N is 2 times 3 times 5 times 7 times 11, yada yada yada, times p, and then add 1 to it. Well, now clearly, n is greater than 1, which implies q divides n for some prime number q. Because q is prime, q must be one of the prime numbers 2, 3, 5, 7, 11, up through p. This means by definition that q divides 2 times 3 times 5 times 7 times 11 times p, because q is one of these numbers. This implies, however, that q cannot divide 2 times 3 times 5 times 7 times 11 times p plus 1. This is by the lemma. Thus, q does not divide n, because we said this was big N. So q divides n, and q does not divide n. This is a contradiction. So our original assumption must be incorrect. Thus, the set of prime numbers must be infinite. So when can we use, or when do we use an indirect proof? Well, sadly, there is no definitive answer to that question. However, the following are recommended steps to take when trying to prove a statement. First, try to prove the statement directly. So generally, this will either succeed, or in trying to do so, you'll come up with a counterexample. However, if you cannot prove the statement directly, and you cannot find a counterexample to prove the statement, then try a proof by contradiction or a proof by contraposition. And these two methods are usually interchangeable. If you can do it proof by contraposition, you can definitely do it proof by contradiction. The converse of that is not true, however. Not every proof by contradiction can be done by proof by contraposition. So that not only concludes our look at indirect proofs, that also concludes our study of number theory.